Okay, now there is something called a brightness constancy assumption. Okay, when once we do the math, right, then it will become more clear. Brightness constancy assumption. Okay, this is an assumption that actually says that when you go from one frame to another, right, then within a distance, right, which is very small, the right, I mean, intensity can be kind of, right, assumed to be the same, right. I mean, so let me just write that down. So for a small space time step, that means both in space and in time, right, you can assume that I of, okay, I is your frame, okay, I is your right, intensity, I of x plus delta x, y plus delta y, and then t plus delta t, right, is equal to I of, right, x y comma t. That means, right, in the right immediate neighborhood, and both temporally and spatially, right. So you can assume that the intensities haven't changed much, which is okay. It is a kind of a reasonable assumption to make, right. And where delta x is u delta t and delta y is v delta t, and uv is actually the optical flow. This is the optical flow at that particular location. Okay, like I said, this u comma v is going to change at right, I mean, every point, at every x comma y. So uv is your optical flow, and right, this is how it is. Now, if you do a Taylor series expansion, a first order Taylor series expansion, then the left, right, you can write this as I of x y comma t plus delta x, and then I'll write this as Ix, right. By Ix I mean a partial derivative of so dou Ix y comma t with respect to dou x with respect to x. Okay, that's Ix plus, let us say, delta y Iy plus delta t, okay, It. Now It will be a temporal, this one, a derivative. Okay, these are spatial derivatives. This will be a temporal derivative. That means this will come from across the frames. Okay, is equal to I of x y comma t. Okay, so this I of x y comma t, right, we can actually remove from both sides, and if you now divide this by this time, okay, delta t, so what we get is delta x divided by delta t Ix plus delta y divided by delta t Iy plus It, right, is equal to 0, right. This is what you get. Now, in the limit that, right, delta t tends to 0, right, then this becomes actually delta x by delta t is your u velocity, right. That is your u component. Delta y by dy by dt is your v component. Therefore, right, this becomes u Ix plus v Iy plus It, right, is equal to 0. This is called the brightness. Okay, right. So this is called the optical flow equation based upon the brightness constancy. Okay, Ux plus Viy, or in other words, right, you can even write this as Ix as actually a dot product Ix Iy Uv, right, is equal to minus It. See, it's one thing that Ix and Iy and It, right, we can actually find out. I think, I have a slide, I mean, right, which we know how to do actually, right, I mean, because spatial derivatives and all you've already seen, and right, this is simply a matter of computing temporal. So we know that, right, if you have an image, say Ix will come from, let's say, within the image, right, because this is like a spatial derivative. Iy will also come from, let's say, within the image. It's just a kernel, right, all the several kernels that we did when we did edge detection, or any of them, but then It is going to be delta I by delta t. So it's like right, I mean, if you want to find out, right, I mean, what is this difference at this location, right, then you just subtract the two, and then you will get like whatever 0 0 0 corresponding to this, and then 10 10 10 minus 1 1 1, that are like 9 9 9 and so on, right. So you have a spatial derivative, and then you also have actually a temporal, this one, a derivative. Now the point is, right, you have only a single equation, right, but then the unknowns are two. See, Ix we know, Iy we can compute, It I can compute, right, between successive frames. correct. I mean, so this has to come from two successive frames. So I have this, but then right, and Ix and Iy are at a point, right. Again, everything is at a location. Okay, UV is at a location, is at a pixel location. Ix, Iy is actually the kind of right gradient at that location. It is a temporal gradient, right, for that location. Now you seem to have a line like this, right. Now if you really plot this, right, then what this means is if I say that this is u and that is v, right, then this equation is like uix plus viy plus it is equal to 0, right. So where I know ix, iy and it. But the point is, right, when you so I know that right. I mean, so if you tell me that if you give me ix, iy and it, I only know that my optical flow value lies on this line. Where on this line, right, I am not able to tell, right, because I only one equation, right. Now I can only say for sure that it lies on this line, but then where it lies on this line, right, I do not know. I mean, right, it could be here, it could be there, I do not know where it lies, right. So kind of there is an ambiguity. But then, right, okay, things are not so bad. So what you can do is, so what we can do is, suppose I take this equation and suppose I scale it by root of ix square plus iy square. So in a sense, right, what I am going to do is, okay, or else I will just write this as ix by root of ix square plus iy square, and then iy by root of ix square plus iy square, and then I have uv, and then I also scale on the right minus it by root of ix square plus iy square. Now what is this guy? So now that I mean, I can think of this as some vector dot product uv, right. Earlier also it was that, but then but this is now a special vector. What is this vector? See, this is Ix and Iy, this is not any old vector, right. This is Ix, which is the gradient, Iy, which is a spatial intensity gradient, and you are kind of right normalizing it by its length. So what will this be? This will be the unit vector in the direction of the brightness gradient, right, at that location, right. So this is the unit normal. This is the unit normal in the direction of the brightness gradient. And this equation, right, and this kind of dot product, gives you, what does it give you? This kind of a dot product, what is it kind of giving you? It is giving you the component of the optical flow along the brightness gradient direction, right. That is what it is, no. So this dot product gives you the component of the optical flow in the direction of the brightness gradient. Okay, but this has a special significance on the right. What is that? This component is this, right, minus it by root, that is the component, right. I have taken the dot product, I get a value, that is my component, which is gives you the component, this component is minus it by root ix square plus iy square, right. That is what I have on the right. No, that is my component, but what is this with respect to that figure? What is it with respect to this figure? Where does it point? Where does this lie? Is this not a perpendicular distance from the origin to a point on the line? That is how you do, no. Ax plus by plus c equal to 0, if that is your line, then the perpendicular distance from the origin to that line is mod c by root a square plus b square. That is exactly what this is, right. I mean, you have this is the equation of the line, right, and this one, right. So this is actually orthogonal, this is actually perpendicular. So what this really means is that, so right, but here is the key point. So what it is telling is, see, if you kind of think about the optical flow, I do not know where it is, right. I told you that I do not know where the optical flow is. It could be anywhere. Suppose it is here, okay, at this location. So I can kind of think about it as having one component, right, which is this, and they say another component which is this. It is a summation of these two components, right, two vectors. So I can call this as p and I can call this as q. This is a vector, this is a vector. So the summation of these two vectors is this optical flow vector. but what you can clearly see is that this P is always the same. See, I mean, right, even if I am here, right, I mean, I can again decompose it as this component and that component. Do you see this? I mean, this is very, very important, right. You can see that the component along the brightness gradient you can always find out without ambiguity. The ambiguity comes only along the parallel flow. The parallel flow you can never find out. With this one equation, you cannot find out the component along the right edge direction. What does it mean? Right? See, that is the orthogonal component. No, I have one component going along the brightness gradient. I am saying that the other component is orthogonal to it. Right? That I am saying I can never find out. What does it mean? That means that when an object moves along the edge, if there is a motion, I cannot find it. Actually, this happens in your human visual system. This actually happens. I mean, this is not something mathematical alone. Okay, this is true. Okay, this happens, and I am going to show you an example where I am going to fool you, right? And you will know that, right? So this is called the aperture problem. Okay, this fancy thing is called the aperture problem. Why do we call it as an aperture problem is because it's like saying that why do we call it an aperture? Because I am looking at a point, right? I am trying to compute optical flow at a point, right? That means you are down to a very, very local motion and you are trying to see what is that motion, right? So if I sort of expand my aperture and if I just make my aperture bigger and bigger and bigger, then I can see a lot more and I can say a lot more. I might not even have this ambiguity. The ambiguity is coming because you are looking at optical flow at a pixel. That means the window, right, through which you are watching it is so narrow that through that window, right, whatever you are seeing, you are trying to base your opinion on that, and that's why it's called the aperture problem. And this is exactly that. And the next slide, right, will hopefully demonstrate that. Let's see. Okay. Now you tell me, okay, based on this motion, which way is the motion? I'll play again. So it looks like it's going this way, right? But let's see the actual thing. This is how it moved. The motion was actually horizontal, right? This is, I mean, right, all of us got fooled, right? I mean, this is nothing. This is exactly the aperture problem, right? Because what you are doing, I mean, see, it's like saying, now I have a larger aperture, right? The outer one is a larger aperture. Now I can see, oh, it's right and all. But the moment I kept the aperture very small, I reduced it to this, then you could not make out, right? This is exactly the point. So what this means is that the parallel flow cannot be found at all with this one equation. Of course, there are ways to kind of get around this, but this is a fundamental problem called this aperture problem. Okay, so you saw an example of this. Okay, so let me just write this down. So so here is the most important conclusion, right? So only the normal flow. Okay, that's called the normal flow. Okay, normal flow, that is the optical flow in the direction of the brightness gradient, in the direction of the brightness gradient. Yeah, there is even this other illusion, right? What is called the Barber pole illusion. Let me see, right, if we can show you that. See this, right? This is called the Barber pole illusion. Look at the left, right? That is a Barber pole. I mean, I don't think our barbers have it, but right, there are places where they have it. So it's actually rotating like this. The motion field is this, but then if you look at the optical flow, it looks like, right, it's all going upwards. Actually, if you look at this bar, right, it's only rotating like this. So the optical flow, the motion field is actually this. So if you see the actual motion field, it should be this. But then the optical flow is exactly orthogonal to that. So there are several illusions. In fact, there is one more illusion Let me also show you, right, while we are on this, that's at the end. I mean, right, this is, watch this. Do you see something moving? But you just focus on any one pixel, nothing will move. There is no change. Right? Can you see that? I mean, I'm trying to see. I think I can see that. It looks like something is moving, but you just focus on one area, nothing is moving. Anywhere you focus, nothing is moving. But your brain is tricked into believing that these are called rolling snakes or something. And there are several such illusions. Okay, this is actually called some drift illusion or something. So so that's why, right, this motion business, we get fooled many times. I mean, right, it's not like every time, even we can be in trouble. Okay, anyway, so that is the optical flow in the direction of the can be exactly determined, and also, right, this is the only component that can be determined. The component along the edge, along the edge direction, what do you call, that is parallel flow. It's called the parallel flow. Cannot be determined based on the single equation. Okay, cannot be determined means, right, based on one equation. Okay.